In this video, I'll say a few things about polynomials and we'll work through a few examples. Polynomials are functions of the following form. They're just a combination, a sum of power functions. So a constant plus x to the 1 plus x to the 2 and so on. So you put a bunch of power functions together, you get a polynomial. They're very versatile functions. They can be used to approximate lots of other functions. And they come up a lot in different settings. So, as I mentioned in class, you'll have this. You'll call this a quadratic equation. And the general shape of this would be something that would look like that. You'll call this a second-order polynomial because the highest power is 2, so second order. This would be a third-order polynomial. It's a cubic. It might look, that would sort of be a generic cubic shape. And then a quartic, fourth-order polynomial that has these terms might look something like this. So one way to write polynomial is something x squared plus something x plus a constant. I could also write it in factored form. So I could take this, and it may be possible to do to rewrite it like this. So you could take an expression like this. If you FOILed it out, distribute all the multiplication, this would indeed be of the form something x squared plus something b plus something x plus something c. Sometimes this form is more useful, sometimes this form is more useful, especially when you're doing graphs. And so what I want to do next is an example of going from a graph to a formula for a function where this form of the function is the most useful one to use. So here's an example. Suppose we have the graph of a function. Here's the function, this curve, and I've drawn the zero axes in yellow to make them stand out a little bit more. And suppose we wanted to come up with a formula, an algebraic expression for this curve. So in this setting, it'll be most useful to think of this in this form. So I know it's going to be a cubic because it has a general shape of a cubic function. So 2 wiggles means it's a third-order polynomial, 3 wiggles means it's a fourth-order polynomial, and so on. So I'm going to have 3 terms multiplied together here. So these terms are just the intercepts of the function, where it crosses the zero axis. So I claim that this is going to be something like x plus 3, x plus 1, x minus 2. So to see this, let's check. So I know that if x is 2, the function is 0. So let's see. If I plug in to this thing, x is 2, I get 2 minus 2, that zeroes out this term, so the whole thing is 0. If I plug in minus 1, then this term gets killed. I've got minus 1 and plus 1, that becomes 0. That zeroes out the function, as we require. And similarly, if I plug in minus 3, I get minus 3 plus 3, that's 0. So that makes the entire function 0. So I know the function has to have this sort of form. We can actually figure out k. We can figure out k by plugging in x equals 0 and reading a point off here. I guess you could plug in any other non-zero point, but it'll be vastly easier algebraically to plug in x equals 0. So let's see. So we want to know now, what's k? Well, what do I know? I know that f of 0 is, let's see, I can read it off the graph. That looks like that's around 3. So I'll say that f of 0 is 3. And then I can plug in x equals 0 and solve for k. So I'm going to plug zeros in here. So I'm going to have k times 3 times 1 times minus 2. This left-hand side is f of 0, and that has to equal 3. So now my task is to solve for k. And this doesn't look like it's going to be too bad. I can divide both sides by 3, cancel the 3's. Then I've got k times minus 2 equals 1. So k is going to be minus 1/2. So we could have predicted the minus sign in advance. So let's stop and think about that for a second. This is negative for large x. We'd say the leading term here is negative. The large x behavior is negative. So that means that a couple ways to think about this. It's an upside down version of the basic shape. There's the basic shape from before. So a cubic polynomial is usually positive for large x, but we'll need to make it negative, so we have to add a negative sign in there. It also means that this term a would have to be negative. If we look here, if we multiply this out, we're going to have a lot of terms, but the big term, the x cubed term, will be x, that's positive x, or and then this k, so k would have to be negative in order to make the x cubed term negative, so that this is negative for large x. So sometimes you'll be given enough information to actually solve for k. Other times you can just say what the sign of k has to be, is it positive or negative, by looking at the large x behavior of the function. Let me work through one more example. So the question before us that we'll consider a couple different ways is, what does this polynomial look like? So first, let me think about just doing a really very rough by hand sketch. So I know that this is cubic because the largest power is 3. It's a third order polynomial. And there are these curvy things. I've got two humps. And I know that it's going to be negative for large x because of this negative sign here. So I think the general shape is going to have to be something like this. Didn't even put axes, but the main idea is when x is very large, this term is by far the biggest. These are all tiny compared to this when x is really big. And this negative sign out here is going to make the whole thing negative. And I know in general that cubic functions look like this. So this would be a sort of zoomed in view. On the other hand, if I was zoomed out really, really far, I might not even notice these bumps. So let me illustrate that with some Wolfram alpha plots. So here's a plot of the function from Wolfram alpha that I screen captured and then printed out. And as expected, it's a lovely cubic function, negative for large x, but positive for large negative x. And there it is. But what I want to do is see what happens as we change these limits, as we look farther and farther out. So if instead of going from minus 2 to 6, and I kind of fiddled around with those limits until I could kind of get all of these graceful arcs here looking nice. So if we go instead from minus 10 to 10, let's see if I can get both of these on the screen, we can start to see that because we see so much of this tall peak, that the little bumps down here almost disappear. And in fact, this just starts to look like a cubic function. It's almost like these terms aren't here at all. Like it's just a minus x cubed. So let me illustrate that with this Wolfram alpha plot. So one of these curves, this curve, is the full function, and this is just the cubic piece. And you can see that they are very, very similar to each other, and you can't really even see those bumps at all. And lastly, if we zoom way out, So now this is x going from minus 100 to plus 100. And these two functions look essentially identical. There's almost no difference between them. Yeah, they're not exactly the same, but they're almost the same. And so what we would say, the math language is that this term dominates for very large x or very large and negative x. That if x is around 100, and certainly if x is 1,000 or 1,000,000, it's almost as if these terms aren't here at all. So if we want to understand the behavior of a polynomial for very large x or very large and negative x, we just need to pay attention to the leading term, the term with the largest power on it, because that's so much bigger, whatever it is, positive or negative, than all of these other terms. And so this idea of thinking about sort of which terms dominate, which are the most important, will be useful when you start doing calculus, and we'll do a couple examples with them at the beginning of class on Monday.